Okay, so thank you for the invitation, and let me wish you all a happy New Year, better than the previous one. Okay, so so the content of the talk is relates to works of Hilbert and Schinzel, and both are concerned with polynomials. And more specifically on the subtopic of specialization. And well, so I'll start with the general context for both, and they are quite easy questions to understand. So the general context. Okay, so let me see. So for the whole talk, I'll have a base field Q, and the two dots are for some assumptions that I'll give later. And I'll have also a ring, a subring Z, and the fraction field of Z is Q. And I have assumptions, but a special case and a typical and maybe maybe most important special case is simply the field of rationals and the ring of integers. And I have two sets of variables, and the first one, the Ti, are those that are to be specialized, and the other one will not be specialized. So the Ti's will be specialized. And I also give myself a sets of polynomial. P on the line is a set, but Pi's are the polynomials in Y and T, and with coefficients in Z. And I assume that they are irreducible in Q of YT, and they are of degree at least one relatively to Y. And well, the specializations is just these operations. I specialize the Ti, so when the capital T becomes a small t, and there are several of them. And okay, so the main issue is are these specialized polynomials irreducible? And I guess you see Hilbert coming. So here's the standard notation. HQ of P is a set of all K tuple, K is the number of variables, T, such that the polynomials are irreducible. And Hilbert's theorem, well, so Hilbert theorem is that this set is Zariski dense in Q to the power K. So if Q is the field of rational, this is exactly Hilbert's irreducibility theorem. And more generally, if Q is Hilbertian, and this is the definitions of Hilbertian. So let me give you some more standard examples of Hilbertian fields, but you may, I guess you all know them. So the field of rationals and the field of rational functions in some indeterminates, and all of their finite extensions. And more generally, any field with a product formula is a Hilbertian field. So there are other kinds of Hilbertian fields, but for these talks, the context will be that, a field with a product formula. So let me with a product formula, and also as also usual, I assume that it's of characteristic 0 or imperfect, because as you know, if perfect is a field, if it's perfect, there is the well, I guess I think the Hilbert subset associated with y to the p minus t is empty, so it's p is a characteristic of the field. So if it's of positive characteristic, I'll assume that the field is imperfect. What is this? Okay, and so Hilbert's theorem is very classical, but with the next thing is also very classical. That if you look for good specializations in the ring instead of the field, it's true too. So HQ of P intersection with Z to the K is Zariski dense too. And if Z is the ring of integers, it's also Hilbert's irreducibility. It was also proved by Hilbert. And in general, there is these definitions of Hilbertian ring when this property holds. And it's also true that if Q is a field with a product formula, then any subring such that the fraction field is Q is a Hilbertian ring. So you can find good specializations with coordinates in the ring of integers. Okay, so now here comes the main theme of the talk. The question is, what about irreducibility in Z of Y, that is over the rings of the specialized polynomials? And well, the difference, as you know, between irreducibility over the rings and irreducibility over the fields is this. So if on top of irreducibility over the fields, you know that the polynomials are primitive. That is, so primitivity means that the coefficients are coprime. Then you can conclude that they are irreducible in Z of Y, and it's also an equivalence if Z is a unique factorization domain. So I'm interested in this question, irreducibility in Z of Y, which on top of the Hilbert's usual conclusions involves some extra divisibility issues on coefficients. And well, if you want to do that, you need to assume that's the least you can do. You need to assume that the polynomials that you started with are primitive with respect to Z of Y. Otherwise, you have no chance to get something interesting. So there are basic counterexamples situations that should be avoided. So consider these polynomials, t squared minus t, y plus t squared minus t plus 2. When you specialize the t to any integer, then the polynomial is always divisible by 2. And so there is another similar situations with these polynomials, t to the q minus t plus u times y plus t to the q minus t. And here the base ring is fq of u. Then if you specialize t to any polynomial, any t of u in fq of u, then it'll be, the specialized polynomial will always be divisible by u. And so to avoid these obstructions, we introduce this definition: an element little a in Z, not a unit and not zero, will be said to be a fixed divisor of P of yt, and I forgot with respect to t. If when you specialize the t to anything in Z, then you always get the zero polynomials mod a. So here 2, for example, 2 is a fixed my is a fixed divisor.
Pierre, this is what some people call local abstractions. It's the same.
Maybe, yeah. This.
I mean, in Schinzel hypothesis H, you have.
Yeah. It's a, and I'm going to call this the Schinzel obstructions or Schinzel condition in a minute. And here it's U, which is a fixed divisor of the polynomial. So with this definition, I think I can state the first main theorem. Okay, so the first main first main result. So assume that, as I said, a Q is a product formula and is of characteristic 0 or imperfect, and Z is a UFD. So if you give yourself some polynomials as before, so irreducible and primitive, then you have this conclusion. If the product of the polynomial has no fixed divisor, and I think that's what Lille refers to as the local obstruction, and this I will call it the Shinzo condition, and we'll see where this reference to Shinzo comes from in a minute. Shinzo condition. So if this condition is satisfied, so no fixed divisor for the product of the polynomial, then you have what you want, that is for, you can find a Zariski-Dense subset H such that for every tuple M in H, when you specialize this polynomial, they're irreducibles in Q of Y and primitive with respect to Z, and so they are irreducible in Z capital Y. So this is what we call, I forgot to say that, but it was on my first slide, that it's a joint work with a few people, Salah Najib, Joachim Koenig, and Arnaud Bodin. So we call this the Hilbert-Schinzel property, and I say it as the versions of Hilbert's irreducibility theorems over the ring. That's okay. So and yeah, about the assumption. So the assumption is that the assumptions on the ring is that Z is a unique factorizations domain, and we can actually and it's actually important to relax this assumption. We don't use the full unique factorization property. And what we really need is this. So an integral domain Z is a near, we call that, maybe it's not a good name, but it's a near UFD if every non-zero of Z, if non-zero element of Z has only finitely many divisors, and every non-unit has at least one. So of course, these two properties are satisfied if Z is a unique factorization domain, and what we this definition actually is interesting because a unique factorization domain is also Noetherian, and if you, in fact, we have an equivalence. Noetherian is exactly what lacks NearUFD to be a UFD. And so we just need the NearUFD part. So every non-zero has only finitely many prime divisors, and every non-unit has at least one. So let me get back to, so I can erase this and write. So this first statement is true for Z near UFD. We also can.
Pierre, sorry, quick question. So would this work for delegate domains?
Well, that's what I have
yeah, I see
here.
now. Okay, thanks.
And so we have it works partially. So for one polynomial and one variable to be specialized, we don't know if it's false, but that's the best we could do. All right, and so about these Schinzel conditions that I introduced, we have this this remark. In fact, it automatically holds, and so you can omit this condition if the ring has this property that every principal prime ideal Pz of Z is of infinite norm. So typically, it's not satisfied for the integers, as we know and as we just saw. But if you take for Z rings of polynomials, then it's always satisfied unless this very special case, and for which I gave the second example. So R should be FQ, and there is only one variable. But except for this special case, it's always true for a ring of polynomials. So the Schinzel condition is well understood. Okay. Now I'm gonna now explain why we refer to Schinzel, and there will be three reasons and three connections to our main theorem. So what I'll start is briefly remind you of the Schinzel hypothesis, which is a classical thing too. Let me start with two famous open problems. The first one is, are there infinitely many primes of the form a square plus one, y square plus one? This is not known and this is out of reach. And the second...
Pierre, maybe you want to scroll down?
Yeah. Let me... It's a new...
Thank you.
So the first problem is this: are there infinitely many primes of the form square plus one? And the second is even better known. It's the twin prime problem. Are there infinitely many m such that m and m plus 2 are primes? And the Schinzel hypothesis is a generalization of these two statements. So if you give yourself S polynomials that you assume to be irreducible over the integers, and you have this Schinzel condition, the product has no fixed divisor with respect to t. And the conclusion is that then you can find infinitely many m such that p sub 1 of m and p sub s of m are simultaneously prime numbers. Okay, this is a Schinzel hypothesis, and well, it's out of reach, as you know. There's only one known case, which is the case where you have only one polynomial and P1. The only polynomial is AT plus B, and in this case, it's Dirichlet theorem, so primes in an arithmetic progression. Well, let me now just make several remarks. The first one is that what I call the Schinzel hypothesis, what I call the Hilbert-Schinzel is just the Schinzel hypothesis in the situation that Z is Z, K equals 1, and N equals 0. So let me show you, this is the Schinzel hypothesis. And let me get back to the main result. It's exactly the same statement, but in the special case that you don't have the variables y. So Schinzel hypothesis is Hilbert-Schinzel in these situations, but I'm sorry to disappoint you. I'm not going to prove the Schinzel hypothesis today. N equals 0 is excluded in our theorem. So what I'm going to explain says nothing new on the on the Schinzel hypothesis. Okay, so let me see where I am. So I'll get to the second reasons why there is a connection with Schinzel, and it is weak versions of the Schinzel hypothesis, something we call the co-prime Schinzel hypothesis. Let me explain. So second reason. So I'm going to consider the special case of the general context for which the polynomials are of degree 1, okay, in Y. So that is that the polynomials are of these forms: Q1 of T, Y sub 1 plus, so it's a linear combinations of the variables Y. Okay, and for simplicity, I just take one polynomials, and also, as you can see, there is only one variable T, the variables that I will specialize. So the Hilbert-Schinzel property, so the first main theorem that I shown to you, in this particular case, is this. So I assume that Q is as before, that Z is a near UFD or a Delegate domain. These polynomials are always irreducible over the fields, even when you specialize, because it's of degree 1. And so the only thing you need to make it irreducible over the ring is to assume that they are coprime in Q of T. Coprime means that they have no common divisors in Q of T other than the units. And on top of that, you have the Shinzo condition, which is no fixed divisor. But in this particular case, it means that no non-unit of Z divides all value Q1 of Z, Qn of Z. Okay. And if you think just a little bit about it, it just means that if you look at all values Q1 of Z, Qn of Z, when I ranges over 1 up to n, and Z ranges over Z, all these values are coprime. And so in this, so the conclusion is then that there exists M in Z such that P1 of M, Pn of M are coprime. So this is the exact translations of the first main theorem. In the special case, Z, the degree is 1. And that's
so Schinzel H implies this, right?
Yeah.
To put it in a level of difficulty.
Exactly.
So Schinzel H is infinitely, is the most difficult problem.
It's a weak version. It's a coprime version. So it's more difficult to make a prime, to make an integer prime than.
Yeah, but if it's a prime, it's automatically coprime.
Yeah. And so, you understand why we call that a coprime Schinzel hypothesis. So let me try to do something. Wow, good. So this is what we call the coprime Schinzel property. And this can be summarized by, the theorem can be summarized by saying that under the Schinzel condition, coprime polynomials assume coprime values. I have a remark about the field Q. I said that Q is as before, but as before means that it has a product formula. But for this particular case, we could actually prove that Q is absolutely arbitrary. It's also interesting to note that so Q is arbitrary, but Z is a near UFD. I mean, there are some assumptions on Z. It's interesting to see that the property holds all over other rings than those that are in the assumption. So, for example, we prove that it holds over the rings of entire functions. And it's also interesting to note that sometimes it fails. So we prove that the property fails for the ring Z with the square root of 5 adjoint. And yes, of course, you might wonder whether there exists, how big is the set of good M? At least, I mean, there's not just one, but you can find infinitely many of them. Okay. Yeah, and I have one more remark about this, which is that, so this coprime Schinzel property, when Z is a principal ideal domain, is easier, and it actually was known before. In the case of integers, it's a result of Schinzel in 2002. And in the case Z equals the integers or FQ of U, it's a result by Poonen. And Poonen has something more. He proved he also gives an estimate of the density of good M. But in this case, what we were able, so in the particular case, Z is a principal ideal domain, we could prove a stronger result, that is this one. So for these problems, you don't have the polynomial speed. It's just a polynomial. It's just questions about polynomials Q1 of t, Qn of t, and so here the idea is that I look at the GCD of Q1 of m, Qn of m, and I call that D sub m, and then I look at the set of all these integers, or I mean integers if Z is the ring of integers, but all these elements of Z, the dm when m is Z. Then what we noticed is that if they are coprime, as we assume, then D is finite, which is quite easy, but it's also stable under GCD. And so that's quite interesting that it's stable under GCD. So the stability is implies the coprime Schinzel in a very easy way, because so in this stronger results you have no Schinzel condition. Now if you put in the Schinzel condition, so the Schinzel condition, what does it mean? It means that all values assumed by the polynomials are coprime. So it's exactly saying that the GCD of all these integers, the D sub m, is 1. And so if you know that this set is stable, then it just means that 1 is itself in the set D. And that's exactly what you want if you want to prove the Schinzel property. And so the PID case is easier. and you get a better result. But and this better conclusion fails for the UFD. We have a counter example. Okay, so now I'm let me check time. I think I'm at the point where I should tell you about. I don't have anything left on this sheet. So I remember I had three reasons, three connections with Schinzel. So let me get the last one. The last one is this. I said that I will not prove anything new on the Schinzel hypothesis. That's not exactly true. I'm going to show you the Schinzel hypothesis for polynomials. So the idea is, so what is the Schinzel hypothesis for polynomials? So here I copied the Schinzel, the standard Schinzel hypothesis for the integers. And what I'll do is that I'll replace Z by the ring Z of Y everywhere. Okay, and here too. Yeah, the Schinzel hypothesis was stated for the integers, but what I'm just saying is that it can be considered for any rings. So this is not anymore the Schinzel hypothesis. It's the Schinzel. What I'm writing is the Schinzel hypothesis for polynomials. My tablet is not working quite well today for some reason. So of course, prime numbers become irreducible. In Z of Y. And one more thing about the Schinzel condition. The Schinzel condition here actually can be, is not needed because of what I told you a few minutes ago in the case of polynomial rings, except for FQ of Y. Then it is automatically satisfied. So the Schinzel hypothesis for polynomials look like this, and there is one more thing that I want to change. So infinitely many integers. Here we thought that the analog of this condition is that there should be elements in Z of Y with arbitrarily really high degrees, partial degrees. Let me write this down. Arbitrarily large degrees.
Yeah, here probably if there is some density, it should be density 1 in contrast to the previous one.
Yeah, we have we actually, I mean,
because polynomials tend to be irreducible, but numbers do not tend to be prime.
What did you say?
I'm saying that probably here the density should be 1 if the ring has some
sure.
natural density.
you're right. But you
because
absolutely
polynomials
right.
are different. Polynomials over an infinite field are different from.
And we do have. I'm gonna tell you. I'm gonna show you the results that we proved. But
Thank you.
And I'm gonna stick to the analog of the Schinzel and hypothesis. But in the paper we have not a density, but we have a better result. So this
Yeah,
is.
I also have a question. So what are the conditions on Z here?
So the conditions are those that I had at the beginning, which is that the fraction field of Z is Q and Q as a product formula.
Mm-hmm. Okay.
Let me get to where is it? So here it is. Schinzel hypothesis for polynomials. So this the assumptions are the same as before. Q as a product formula and is of characteristic 0 or imperfect. Z is a near UFD. UFD if you want to make it simple. And the polynomials are polynomials in variables y and t. There is for the Schinzel hypothesis, there is only one t. And so the statement is that there exists m of y in Z of y with arbitrarily large partial degrees such that pi of y, m of y is irreducible in Z of y. And if Q is of characteristic 0, then you can even require that m of y is of any prescribed partial degrees, sufficiently large partial degrees. So you can fix in advance the partial degrees of m of y that you want to achieve. So that, and we have not a density, as I said, but we have a more precise result in the paper. And yeah, I have some, I think I had some remark, but I forgot where they are. Okay. It's strange. Well, let me make a couple of remarks. Where is it? Ah, here they are. Yeah. So this Schinzel hypothesis for polynomials that I just showed you, with the assumption that Q is a product formula, fails, of course, if Z is an algebraically closed field, which this is obvious, but something that is interesting and less obvious is that if you consider the case Z is F2, the field with two elements, then there is an old result by Swan, this one, that if you consider this polynomial t to the 8 plus y cubed, then for every m of y to the 8 plus y cubed is always reducible. And so the Schinzel hypothesis fails for this ring. But what's also what makes this even more interesting is that if you restrict to the degree 1 case of the Schinzel hypothesis, which I said is Dirichlet theorem, then FQ of y is no longer an exception. Dirichlet's theorem is known to hold for fq of y, so it's an old result by Landau. And there was a result, more recent, proved by Lille, that extend this Landau-Korn-Bloom results to PAC fields. I think there is a technical assumption that should be added, which is, I don't remember exactly, but the case of PAC field was studied by Lille, and basically the Dirichlet theorem holds in this case. Well, so since we have the Schinzel hypothesis for polynomial rings, with some assumption, with the same assumptions, all standard consequences of Schinzel hypothesis, the twin primes, the y²+1 problems, can be hold over for polynomials. And let me give you another one, which is the Goldbach problem. And so using it's not a direct consequence of the Schinzel hypothesis, but using the same techniques, we were able to prove that every non-constant polynomials can be written Q equal f plus g with f and g reducibles in C of y of degree less than degree of Q, and we can even take for f a binomial. Okay, in order to get something on the Goldbach problem from the Schinzel hypothesis, you just put yourself in this situation. So in the Schinzel hypothesis, you can take two polynomials, and I take this one. P1 is t, and P2 is q of y. Q is the polynomial that is given, q of y minus t. The Schinzel will give you m, such that when you substitute m for t, you get your f, and q minus m will be your g. This Goldbach problem statement for polynomials was known in one variable, and it was a result by Pollack in 2011 with a different method.
So did Pollack state this in this generality, or he just handled finite fields?
I think no. I think the generality is even bigger, but he sticks to one variable.
So yeah, you worked with R being something like a Noetherian with infinitely many primes. I don't remember exactly.
So yeah, and the use, but the number of variable is one in this paper. But it's true that his generality is even bigger in this special case. Okay. Again, I think here in everything I said, I think if you want to have a good idea of the assumptions, I think one of the most interesting cases when z is z of y. Already this case is because what I said to start with is you have these divisibility issues on the coefficients, and which are already typical in this situation. Let me see. Well, maybe I have just a little time to say a few words on the proofs.
Pierre, in this case of z of y,
yeah,
that you mentioned, so did you prove in this case the coprime Schinzel?
Yeah.
So it's not about the coprime; it's about the implication.
What implication?
So you mentioned now a special case where the ring is the integers, polynomials over the integers, right?
Yeah.
So what is known and what is open in this case?
Everything in this, the general context for the talk was z of. Let me get back to it. So you see, everything is true when the base ring is Z. So for the Schinzel hypothesis, when the ring is Z of Y, okay, you should really see this as that.
Mhm.
And I was just saying that this Z equal the ring of integers is a special case, but it's a typical special case. And to my taste, it's the most important special case.
I see, now I see. Okay. So you mentioned that in this case already all the ingredients take place.
Yeah, yeah.
Okay, thanks.
It's
I didn't understand anymore.
It's not easier. It's not easier for the ring of integers. And it's, I think, and again, to my taste, it's most interesting. It's even more interesting over the ring of integers for the Schinzel hypothesis, and also even for the coprime Schinzel hypothesis. So I wanted to. So very quickly, some ideas for the proof. So the strategy is quite simple. What you want to do is to prove a primitivity criterion for specialized polynomial that is compatible with the usual Hilbert specialization property for fields. You want to have both at the same time, so for Hilbert-Schinzel, for the Hilbert-Schinzel property, the first statement that I gave you, this criterion is precisely the coprime Schinzel hypothesis. Here's the problems. You have some polynomials who have this form, and you want to specialize capital T to this small t, and you want to use the usual Hilbert theorems for these polynomials, and the Schinzel property will give you some t such that the coefficient are coprime. So that's exactly what you want to do. You want to have both, and the only thing you want to check is that you can do that at the same time. That you can combine the two things. So basically, proving the coprime Schinzel property is the main thing. So that's what I said here. For the Schinzel hypothesis, the last one, which very much looks like the first one, but with some difference. It's a different criterion, and I'm going to show you. It's a different criterion based on new versions of Hilbert's irreducibility with some additional congruence conditions. And I think this statement could be interesting for its own sake. Let me just, if I can find it. Here it is. So in order to prove the Schinzel hypothesis for polynomials, what we did is that we proved these versions of Hilbert's theorem. So the assumptions are as before. And you assume, as for Hilbert theorems, that you're given some polynomials. And on top of that, you give yourself a T0 and a tuple A1, A sub k, S sub k with coordinates in the ring Z. So the conclusion is that there exists T with coordinates in Z such that this first conclusion is just Hilbert's conclusion. And the second one, you can also guarantee that Tj is congruent to Aj, the one that were given, mod T0, T1, Tj minus 1. So we have this extra condition, and these are the congruence conditions that allowed us to prove the primitivity part in the Schinzel hypothesis. Well, I have this other statement that explains how I used this Hilbert theorem but I mean, this gets too technical, and I guess I'm out of time. So I think I'll stop here. Thank you.
Actually, Pierre, you are not out of time because we started late.
What?
You are not out of time. You are exactly on time
Ah,
because we started late. So your
Thank you.
planning was perfect.
thank you.
Okay, so are there any questions?